Okay, well, let's actually get a start. So today I'm actually going to talk about the thermal convection in the Earth's mantle. And this is actually my second time to be at CIDR. I spent about a week last year at CIDR. I really enjoyed the process. And so this time I actually signed up for more than 2 weeks. And hopefully we'll have, I'm really eager to learn from everybody. And so I guess here, I want to actually start with a picture of present-day plate tectonics. So we all know that the Earth's surface actually can be divided into several plates, and they actually have a very strong relative motion between them. Okay, so of course the plate motions themselves implies that Earth's mantle must also move, right? And so this is actually just one computer simulation. It didn't really mean that the whole thing is real, and we see the subduction and the downwalling code, downwalling materials, and we also see upwallings. You can see actually it's very complicated, okay? And so I guess I was asked to give a lecture on this, and I figured, well, what should I do? I have about 1.5 hours, and I figured maybe the best way to approach to this to actually tell you something more basic, and that is some simple physical process that actually govern this. And rather than to go through the all these complications, I guess at the end I'll actually probably show one slide about the challenge and current research, current research direction. But mostly it will be really on simple stuff. Okay, so I guess this is sort of the outline of my lecture today. And I'll give a definition of Mantle convection problems, and actually I'll show you 3 example problems, and to illustrate the basic physics of convection. Then, of course, I want at the beginning to make the lecture more interesting. I'll actually give a historic overview and a sort of broad introduction about the problem that we have here. Okay. I should also mention that this is actually this is the first part, and then this afternoon we can actually have the tutorials. And the tutorials actually, as you will see, they're actually highly related to the problems that actually the example problems I discussed here. Okay, we're actually going to discuss a little bit more about the tutorial towards the end of my lecture. Okay, like any field, right? I mean, there's a as a geodynamist, I actually really think that the mantle convection or mantle dynamics is a really, really interesting problem and got a rich history. And so this concept of mantle convection really came a long way. Okay, and actually I want to in review all this. This is basically all kind of what I call the important events in our study of mantle convection or mantle dynamics before plate tectonics. Okay, and so the plate tectonics will be the last sort of my sort of milestone event here that I missed. And so actually I will be discussing basically through this sort of interesting and important events. In particular, I will actually highlight these 2 problems or sort of studies. As you will see, actually, the reason why I will do this. There are some really interesting and important concepts that are actually buried in these 2 problems. Okay, so I will actually start by talking about the isostasy. And well, we know the isostasy probably is one of the oldest concept or idea that developed in the study of the geology and geophysics, right? We know that I guess another interesting thing is about this isostasy is that isostasy is really the concept was really generated out of very careful calculation and very careful measurements. And so here we know that people like Bouguer and Pratt, and they actually compute the gravitational attraction from mountains. In this case, Bouguer actually computed the gravitational attraction from the mountains in Quito, Ecuador, and it's actually about more than 250 years ago. And Pratt computed the gravitational attraction from the Tibet. Mount Everest, and they actually, of course, they both find out or puzzled that the observed or measured gravitational attraction from mountains appears to be much smaller than what they computed. Okay, and then of course, you have people like Boscovich, and then Airy and Pratt himself proposes so-called isostatic models to explain the difference between the calculation and the measurement. And that, of course, the models, so that's actually the key to this idea of isostasy. And you probably all heard about this sort of iceberg kind of ideas. You have mountains, actually mountains have roots. And I'm not going to repeat on that, but there's actually a very important idea behind all this. That is, basically the implication here, the substrate below the crust is what actually Herschel called the sea of lava. Okay, that means that in the deep Earth interior, even back then, was recognized that for this to be true, and they have to be very weak or maybe sea of lava. Okay, and so that's actually the very first important concept for mantle convection. That is, somehow the Earth's interior is actually very, very weak. Okay, now let's actually talk about this second interesting idea or important idea in the study, in the development of mantle convection study. Okay, so we all heard about the Kelvin's sort of underestimate of Earth's age, but actually wasn't very little discussion about John Perry's sort of critique of his of Kelvin's work. But I guess recently, Phil England, Peter Mola, and Frank Richter actually wrote a paper, very interesting paper, kind of retell the story, a history a little bit about this. I'd like to share with you, about some of these ideas there. Okay. Well, I should say that John Perry actually, he was an assistant to Kelvin, Lord Kelvin, for years. To estimate the age of the Earth, Kelvin actually come up with a very, very simple idea, or simple model. That's actually essentially the heat conduction problem. Okay, and that is to say that if you look at this diagram, this is the depth, that horizontal axis is the time. Let's say at the 0 time, the beginning of the Earth, and the rock is uniformly hot, okay, molten, right? And then if you maintain the surface temperature at 0, then we know that you're going to have a cooling from the top, and you start to develop this thermal boundary layer, okay? And then this boundary layer thickness, thermal boundary layer thickness, can be written as this kappa T. T is time, kappa is the thermal diffusivity, and there's a square root there, okay? So this actually, the whole process can be basically solved by considering this conservation of energy, in this case with heat conduction only, and it's a very, very simple problem. Question we have here, and you can solve this, and the temperature as function of time and the depth, and basically is given by this so-called error function. Okay, so you can actually, with this error function for temperature, you can actually solve for surface heat flux. Surface heat flux Q here is just the thermal conductivity K times the temperature gradient at the surface, right? And you put all this together, and you actually got something like the K Tm, this is actually mantle temperature, divided by basically square root of kappa, pi kappa T, okay? So just let you know that I want to emphasize that this delta, which is the boundary layer thickness, basically can be written as the square root of kappa T, okay? And so you can see the square root of kappa T then has the length scale, okay? And this is sometimes we call this thermal diffusion length scale, or thermal boundary layer thickness. Okay, so if you actually take this, if you take this equation, okay, and you can actually just say take surface heat flux as a Q0, let's say for present day, and then you can actually solve for the time. Okay, it takes for this cooling process to deliver the present day heat flux at surface, right? So then you actually, so this is essentially Kelvin's calculation, and this is with this equation you can actually estimate the age of the age of the Earth, right? You have the mantle temperature, the starting temperature, and you have conductivity, you have diffusivity kappa. Then the Q0 is measured present day surface heat flux, and so of course we know that Kelvin got this round number that's roughly 24 million years, okay. Then, this number actually was much, much smaller than what the geologists believed at the time. And well, what was actually geologists believed at the time was actually it's not a number. Then, well, this number actually was much, much smaller than what the geologists believed at the time. And well, what was actually geologists believed, you really need radiometric dating techniques. And then, of course, then in 1940s, and he come up with the age of the Earth around 4.5 billion years, right? So what's wrong with Kelvin's estimate? So I actually posed 2 questions here. I promise this is the only question that I have here for you. So he ignored radiogenic heating as a heat source in the mantle. That, of course, we know didn't get discovered until 1903, right, by Curie. And the second is he ignored the cooling of the mantle's interior by mantle convection. And you raise your hand if you think that the first one is correct.
I have a question, actually. Did Kelvin express his solution in terms of the error function in 1844? Is that a known analysis?
No, well, actually, I don't think it's actually, I don't think it's actually he expressed expressed in terms of error functions. It's all being discussed in the I guess the Jaeger's book. But this is sort of I guess it's a sort of recount. But the basic idea is the same.
Yeah.
But I think that equation certainly was solvable even back then. Yeah. So there are actually, well, it's good that most of you actually think the second one is correct. It is. You actually can put back, you can actually put the radiogenic heating back into that equation that that I just showed you. It's not going to affect the answer that much. And the key problem is really he ignored the cooling of the Earth's or mantle interior, through the mantle convection. Well,
I think Wikipedia says the first one is just.
Yeah, that's sometimes I check Wikipedia, but so anyway, I show you a video from later on from Wikipedia, and I think that video probably is okay. And so anyway, well, here comes to Perry's criticism. This was published really 1895. So Perry basically sort of indicated that the cooling of the Earth's interior, that is actually below the boundary layer, okay, could actually, this is sort of, we're talking about cooling here, could provide energy source to sustain the observed present-day heat flux for much older Earth, okay? And that if the interior, he actually said, if the interior is a fluid-like, and the convection could basically cool the interior very, very efficiently, okay? And so we know that, of course, this is really the key, right? That you look at Kelvin's model, and Kelvin's model only considered the cooling from the top, whereas because he only considered the conduction. Well, at the time, with no theory of convection, Perry actually introduced this he called the high, quasi-conductivity to represent the efficient cooling from the mantle interior. And well, actually, as Phil England said in his paper, he said, well, if you actually take Arthur Holmes' age determination for the Earth, which is very, very ancient, and then coupled with Perry's argument, and then this could actually be the first confirmation of mantle convection inside Earth's interior. We don't need to play tectonics, really, right? Who needs observations? And so you actually could really just put all this together. We're talking about 1895. That would be actually sufficient, in terms of providing some confirmation of Earth's mantle convection. Okay, so that's actually I thought was kind of interesting, sort of history a little bit there, and then actually, now I want to very quickly talk a little bit about Bernard's experiments for thermal convection and Rayleigh's analysis, okay?
Shijie,
yeah.
Isn't there also the fact that the temperature that was estimated was really high with the conduction? Initial temperature?
Well, I think he will actually, the original calculation, I believe you just assume some initial temperature, right?
Wasn't that one of the problems, is that you ended up with...
Oh, you mean like if you don't consider convection?
Yeah.
Yes. Yes, that would also be a problem. If you have radiogenic heating, and then maybe that will actually heat up the Earth's mantle to really large, to a very large number. I guess in Kelvin's time, there was people didn't know of radiogenic heating. So I guess here, this is actually a movie. I hope it actually works. This is from Wikipedia. So what actually you're seeing here is that, basically it's a very simple experiment anyone can do at home. You have, in this case, is really just 1 centimeter thick cooking oil in a sort of, in a sort of petri dish. Then you put on the sort of electric hot plate, and you start to see the convection pattern develops. Okay. So.
You might point out what's coming up and what's going down in the picture.
Let me actually show you this, and I'll let Mark explain to you. Well, you see the patterns. I believe this is a sort of the down warnings, right? The light colors. And then there's at the center there might be some up warnings. So things going up and down. And it's actually so this is sort of basically sort of simple thermal convection experiments anyone can do. So then of course.
Boundary conditions? What does it do with the edges?
I guess this is probably no steep, no stick. Well, I guess zero velocity boundary condition, I would think. Yeah.
What controls the size of the individual cells?
So you can see the thickness certainly will play a big role, and this is actually a very good question. And we, in terms of we're talking about a convective structure formation, right? And this is a very, very important topic for the Earth mantle. Given that Earth mantle is really long wavelengths in terms of structure, so how you actually produce long wavelengths convection is an important problem. But I guess here, from this experiments, I guess the thickness actually played a very, very important role. Okay. Let's actually. Redi, of course, is a very, very, it's really, really important sort of scientist. I mean, he made huge contributions to our knowledge in terms, if you talk about why the sky is blue, right? And Redi scattering theory really explained that, and he actually won Nobel Prize by discovering argon in the atmosphere. I guess seismologists also really know, radio wave and all that. And then in convection, he actually also made very, very important contributions to Mantle convection by analyzing, basically build up the theory and try to understand the experimental work by Bernard. Okay, and he, for example, he actually really from his analysis he kind of determined the conditions for the onset of thermal convection and so-called critical Redi number that actually I will discuss a little bit later on. And then I also want to point out that when Ballard and Redi, when they study convection problems, thermal convection problems, they really treat it like a general natural phenomenon, sort of really that can be applied to any nature system, right? And Jeffries, of course, we know Jeffries was a very, very important seismologist, and he made a lot of contributions to geophysics, and he also get interest in the convection problem, and he followed up, Redi, and did really made a lot of fundamental contributions to the convection studies. But interestingly, he actually accepted mantle convection, that is convection within the Earth mantle, but he rejects continental drift, and he rejects the plate tectonics. You look at his last edition of the Earth, 1970, and he still didn't believe in plate tectonics. Of course, that was the last edition, fortunately, right? So, of course, now I want to really quickly go, sort of show you this is Wigler's continental drift idea that actually was proposed around 1924. So we all know that. And then again, this is Arthur Holmes. He actually, he is in 1931. He actually wrote a paper to really, to talk about, presented his ideas of mantle convection as a driving mechanism for continental drift. And some of these, ideas he proposed in this paper in 1931, it really captured a lot of the things that we've been talking about today. It was really remarkable, right? I mean, how great, visionary and Arthur Holmes was. Okay. So now, we've been talking about the Earth's mantle, the interior, as the lava of the sea. And of course, if you really want to study that, you have to know the property of that, right? Transport properties, such as viscosity. Is it water or is it what? Under there, right? So then here actually comes, Hesketh's estimate of the Earth's mantle viscosity by, from study of mantle post-glacial rebound problems. Okay, so he came up with a number roughly something like a 10 to 20 Pascal second-ish. Okay, so I want to actually spend some time to kind of discuss a little bit this, simply because really this is you can consider this as a modern analysis, of really like the using the modern analytic techniques to study the deformation and all that, right? Which is highly relevant to mantle convection problem. And so we know that Earth actually frequently got covered by the, especially the high latitude regions being covered by ice, and the ice come and ice, go. And then, this is actually really in the last glacial and deglaciation cycle, and about 21,000 years ago, large part of the northern hemisphere actually covered by glaciers. Then, and since then, they kind of got disappeared. And then, of course, we know that if you actually if you have, this is 3 different time frames, if you actually remove the ice, of course, when you first glaciate, during the glaciation stage, and the ice actually causes the subsidence of the crust, and then the mantle material below, and of course, will move away, right? And then you kind of melt ice, and then basically the mantle will rebound back, and the mantle material actually move back to the formerly glaciated region, and then eventually, and then you actually will level off. Then everything stopped, right? In terms of the rebound process, and so that's actually I guess I said, and this rebound process is actually something that you can measure. And for example, you can go to Hudson Bay, you see this kind of raised beach, okay, from this formerly glaciated region, and so you can go to date these beaches, and then you actually can figure out the rebound rate, okay. So then people have studied the problem. And try to use this observation to estimate the mantle viscosity, right? For now you can say almost 80 years now. And so here I want to actually really show you a very, very simple analysis. And and probably you decide. Probably I wouldn't even call it analysis. Just some really simple estimate, order magnitude estimate. It's actually not bad estimate. But it really captures the sort of essence of this. So let's say we have after deglaciation, right? Let's say there's a big hole here, and let's say the horizontal length scale of this hole is L, and let's say the depression is H here. Let's also assume that the delta T is a sort of typical rebound time scale. Okay, this could be 10,000 years, right? And we know the viscosity, is defined. The eta viscosity is defined as basically the stress divided by some kind of strain rate, eta. And stress is, it's, I guess mathematically it's really sort of a tensor because it really describe forces on a surface. And so, which means that, force got 3 components, and if you want to describe a surface, you got another 3 components. So, that's why actually stress is a tensor. And here, of course, because actually it's a sort of like some kind of surface force, I actually got a unit of force per unit area, or Newton per meter square, or Pascal. And in this problem, the relevant mantle stress, that is stress here, we can actually use basically rho GH here to represent the relevant stress in this region, order magnitude. Okay, you see the rho GH also give you the right unit, right? Give you and the strain rate basically describes the rate of deformation with unit of per second. And so therefore, the viscosity is stress divided by strain rate, so you have Pascal second. Okay, that's sort of the unit for viscosity. And then in this problem, we actually basically can use H over L as some kind of measure of a strain. Okay, then you divide by delta T. That's actually your strain rate. Okay, order magnitude estimate. And you put all this together, and you actually come up with a viscosity that is rho GL multiplied with delta T. Very, very simple, right? You put the numbers like delta T 10,000 years, L 1,000 kilometer, and then you got something like a 10 to 22 Pascal second. This is one order magnitude off from Haskell, sort of typical number. And it actually turns out that the rebound process, if you actually really go through the detailed analysis for let's say still some kind of half space problem, and you actually see the rebound process itself is an exponential function of time. And so there's a geometry considered, and you have to put like basically 2 pi under here, okay? And so that's factor of 6, right? And then the delta T actually is not really delta T. It's actually, it should be like a characteristic time of the relaxation process. So it should be less than 10K. So if you actually really consider the detailed analysis, you'll get about something like 10 to 21 Pascal second. But this basically gives you the essence of what's going on here, okay? And so, anyway, now the plate tectonics, everybody knows this. And so that was a kind of quick overview, but essentially sort of the development of the key development of the Mantle convection ideas of study. Yeah.
Quick question. So most of these glacial rebound studies are done on the thick parts of continents.
Yeah.
Is it possible that we overestimate the viscosity of the asthenosphere that way?
I think it is highly possible that this is the sensitivity is such that the rebound process are primarily sensitive to local viscosities. And I think that's been demonstrated in the last 10 years also. So it's not very sensitive to like oceanic regions. So that is something we have to keep in mind, yes. Okay? So now the history is history. If you actually don't have any question, now I'm going to move forward, okay?
Why waiting 35 years for plate tectonics theory?
Oh, I was not there, but I don't know. I mean, it feels like observation is still important, right? You need people are more convinced when they see things move around at the surface. It's like I guess another way to say is if your neighbor kind of dig a big hole in his own sort of backyard, you probably wouldn't necessarily care. But if you start to kind of dig into your basement, then you say, oh, what's going on? I start to feel that. And you start to care. Yeah. I don't know. Yeah. So now actually I want to actually just give a quick definition of Mantle convection problem. That's sort of problem that we actually deal with here. We can actually say that mantle convection is really a physical process within a planetary mantle that controls the heat release from and the structure formation within the Earth, within the mantle. Thus determine the evolution of planets and their surface geology and tectonics. Okay, and you can see I'm sort of really exaggerate the importance of mantle convection, right? But that's actually really what I believe. I mean, it's really important. So the basic theory really, I mean the basic one. I'm not talking the simplest version of the theory. It really consists of conservation laws of mass and momentum and energy, and considering mantle as a viscous fluid. Okay, and a good example can be found from basically Mackenzie 974, and this is sort of this equation is the conservation with mass. Okay, we call it sometimes continuity equation. Don't need to worry too much about this. Just I found it's actually easier to point out certain terms here, so I use this equation. And then since the Earth's mantle fluid actually is so slow, and we actually can ignore the inertial effect. This is sort of acceleration effect, right? And so then if you look at Newton's law, if you ignore the sort of acceleration term, then essentially becomes the summation of force equal to 0. So we call it force balance. And so you can see here, and this momentum equation or conservation momentum essentially is it's just a force balance. So you have this gravitational force, rho g, right? And then this force actually is related to the stress, or the surface force related to the stress, okay? And so it's really just the force balance, right? And then this is energy equation. We actually already considered energy equation earlier, like in Kelvin's sort of, that problem, conduction problem, right? Now, the new terms are, we have this convective heat flux, or convective heat transfer term here, U, this is velocity, dot the, sort of multiplying the temperature variation, and there's this actually radiogenic heating term there, okay? And now this is sort of basically the energy equation. So, of course, we somehow have to consider equation with state, that is, basically relate the density variation, or the density with some kind of temperature, okay? So this is really a thermal expansion. And then we always like to non-dimensionalize the equation. I mean, I guess another reason that I showed this is because this afternoon, we actually, the students, especially if you're going to do tutorial, we need this, okay? And so the tutorial, the computer code really solves this non-dimensional equation, okay? I guess part of the reason that I showed this to you. I guess you can see the non-dimensional equations are, essentially similar to the dimensional equations. One thing that is actually quite important here is, there's this Rayleigh number that is actually here, okay? The Rayleigh number is really defined by this expression. Then this is the density of the mantle times the gravitational acceleration g, and the thermal expansivity alpha. Then delta T is some kind of a temperature scale, okay? And you can say this is a temperature drop across the mantle. And the D here is the thickness of the mantle, okay? And then the eta 0 is the viscosity, kappa is thermal diffusivity, okay? And this number is really, really important in Earth mantle convection, or in planetary mantle convection problems. You can actually view this as a ratio, some kind of ratio of convective driving force to resisting force, okay? And this also determines the convective vigor. The larger the viscosity, the larger the Rayleigh number, and then the more vigorous the convection can be, okay? And for the Earth, if you put in all the numbers for the Earth, like viscosity 10 to 21 pascal second that I was talking about earlier, and you'll come up with something like 10 to 7, 10 to 8 for present-day Earth mantle, okay? I just want to actually point out here a little bit. So you see the viscosity and the diffusivity, actually they appeared in the sort of denominator, right? So you can see the large number of those two will actually kind of reduce the Rayleigh number. So it means it's not good to have. If you want to have convection, it's not good to have large viscosity. It's not good to have large thermal diffusivity. Those are actually kind of really retard sort of convection. Okay. So that's about all I want to say about the theory. Okay. From now on, I guess really, unless you want to do the tutorial this afternoon, and you probably won't see, really wouldn't need to care about this much. Okay. Do we have any questions? Yes.
Question about that. At least in some materials, the viscosity and the thermal diffusivity are going to be actually correlated, right? Because if you look at, let's say, the core or whatever, it's going to have a low viscosity, but be highly conductive. If you look at the mantle, it's going to be more viscous, be less conductive. Those are going to tend to balance each other out a little bit. I wonder if there's some sort of scaling there that applies.
That's a good question.
Mark knows something about this, right? Or is he awake?
No, I'm awake.
I mean, I guess the thermal conductivity and the electric conductivity, they're certainly related to each other.
They're linearly related.
Yeah, I guess the viscosity. The viscosity, I wasn't so sure. I mean, I can see they're possibly related to each other. I mean, the defects will help with both, probably, right? But I guess I don't know if any other than hand waving. I don't.
It's easier to relate.
Yeah.
I was just going to say, I mean, Rayleigh number is very sensitive on this length scale, d cubed. When you have a given problem, can you say a few words about how you recognize, identify the appropriate length scale?
Well, the d is the thickness for the Earth, for the thickness of mantle, right? So if you think it's a whole mantle convection, that will be 3,000-ish kilometer, right?
Okay.
Yeah.
Right. I guess
sense what Gene says, right? There's also some utility in thinking about local relativity.
Oh yeah, we'll get it. We'll get there. Yeah, we'll get there. Yeah. So absolutely, yeah. Yeah.
Has delta T been grossly different from 4,000 degrees?
Well, with uncertainty, 20%. 4,000 Kelvin, seems to be the number that people like to use for the Earth, for the Earth mantle.
But for these two, I think you want to take out the 80 band.
Yeah, that's true too. You have to, right. So that would be maybe 25 or 2,700. Yeah. Yes?
Was that Lou who asked the question about the correlation between Yeah. So, one thing to keep in mind there is that the viscosity depends strongly non-linearly on most of the things that we care about,
right.
Like temperature and water
Yeah.
content and so on. Whereas the thermal diffusivity doesn't. And you can see that in the equations because the thermal diffusivity would be in the del squared T there on the lower, on equation 7. Next to it, it would be in front of the T on the Q, T plus Q, right, on the right-hand side. And it's not, it's basically where that equation is written to assume that it doesn't vary at all. Right?
Yeah.
It's
Yeah.
pulled out.
Yeah.
And that's a reasonable assumption for the Earth. So
Yeah.
that, yes, it does vary with composition. Those two things vary together with composition. But for the mantle, what really matters is the variation in viscosity and not really the variation in
Yeah. I mean, I guess here, I kind of put the viscosity still in this sort of bracket. So, but I suppose it can actually be variable even in this equation. But it's true the viscosity is really a big headache in mantle dynamics study, and it's a lot of it's a very important parameter. There are also a lot of uncertainty with it. Yeah. So now, I actually want to really show you how I'm doing time-wise.
Another 15 minutes.
15?
15 minutes altogether, including...
50. Oh, okay. Well, that's good enough. Yeah. So it's like non-list, but it's really we can go through fairly quickly. And so now I actually want to just really present you 3 example problems to So the hope here is really it's not to show you the complexity; it's really to show you the simplicity. And so we can actually get something home that still feel like we actually understand something. Although you'll probably find the conflict, from the reality, but still understanding is more important. So the first problem that I actually will be talking about is really this condition for convection to occur, the critical Rayleigh number problem. Okay. So I guess I showed you this YouTube movie earlier, and so you can see that the convection can happen. Of course, there must be some condition under which the convection can happen, right? For example, you need to put this on a hot plate, right? It's not like just happen any circumstance, right? You have to provide heat, and you can envision if you have a different fluid, it may actually show up differently, right? So the question that we posed here really, what are the required conditions for convection to happen? What is the sort of physics behind it? Okay, that's really what we're kind of question that we're asking here. And so often this onset of convection problem or instability problem can be posed in this way. Okay, this is you look at Turka-Schubert, and this is what the problem being posed. Suppose you have surface temperature T0 is maintained, and then the bottom temperature TB maintained, and there's this layer of fluid with a thickness of D and with all this density, thermal expansivity, thermal diffusivity, and viscosity, and with gravity, of course, pointing downwards. And you kind of assume, let's say you ask, okay, suppose this actually already reached to some kind of steady state, such that the temperature is a sort of linear function of depth here, okay, surface 0, and at the bottom is TB, okay. And you ask yourself, if you perturb this system, and what conditions and this thing, the convection will start, okay. That is, you start to see the circulations, and that's really the kind of question that we kind of posed here. It turns out that actually this onset of the problem can be conveniently expressed in terms of Rayleigh number. really started this problem, right? He analyzed the problem, so we kind of named this after him. So the Rayleigh number is really, I showed you this earlier. I said that, this Rayleigh number will actually show up, repeatedly, and this is the second time around showed up. It probably show up like 10 times during this entire lecture. So it's rho g alpha, it's all kind of relevant parameter here, and the temperature, the differential temperature across this layer, right, and the thickness cube of this layer, and then the viscosity and the diffusivity. Okay, it turns out that when this number, whatever fluid or whatever material you work with, whatever the geometry you have, it turns out that if you somehow the combination of these parameters give you the Rayleigh number, if that Rayleigh number is bigger than something we call the critical Rayleigh number, which is typically on the order of 10,000-ish, 1,000. Yeah, typically on the order of 1,000-ish, and then the convection will start. Okay, so the system is unstable. And then when the Rayleigh number of systems is smaller than this number, critical Rayleigh number, then you don't see convection. Okay, and so this is really sort of the if you go through the analysis, you check on Torka-Schubert, and that's what you actually see. Okay, I want to actually present you a really simple analysis of this problem, without going through all this complete mathematics. Even for Torka-Schubert, I think it will probably take 2 lectures to cover that whole analysis, right? So I'll actually just give you like a few minutes kind of discussion on this, and so the idea here is really to develop some physical insight of this problem. So let's actually consider a sphere, okay, a buoyant sphere. So if the delta T here is a differential temperature between the sphere and the background. If delta T is a positive number, so then the sphere is buoyant, right? And so if it's buoyant, of course, we know there's a deficit of density, that it can be written as basically the rho density multiplied with the thermal expansivity, then times this differential temperature. And so we know that since it's buoyant, and so the sphere will rise, right? In the under the influence of gravity. And let's say the speed at which the sphere rises is v here, okay? And we also know that due to the viscous drag, the background medium is viscous fluid, and so due to viscous drag, and then there actually will be a certain region that actually will be kind of dragged along with the sphere, right? So let's actually assume this region with a length scale of L, and the L could be on the order of R, okay? R is the radius of this sphere, right? And so let's actually first, sort of consider this. Often we call the Stokes sphere problem. We really consider what is this velocity, rising velocity for the sphere with this kind of geometry, with this kind of buoyancy field. Okay. So as I guess I mentioned to you earlier that one of the governing equations that we consider is conservation momentum. That's a sort of fancy way to say it, but really what is just the force balance, right? Since we don't have the inertial terms. And so if we consider the force balance, there are essentially 2 forces acting on this sphere. One is gravity, right? That is just simply mg, right, gravity. And then other is actually the viscous force acting on the sphere. And the viscous force, of course, tend to drag the sphere, retard the fluid motion for the sphere. And so if you consider the viscous stress in the medium as a sigma, then the viscous force acting on the sphere, you will have to multiply that with the surface area of the sphere, 4 pi r squared. And then this actually will give you the total sort of resistant force acting on the sphere. And then in terms of gravity or the buoyancy force, that's just simply the volume of the sphere, 4/3 pi r cubed, then multiply with the deficit of density delta rho, and then you multiply with g, the gravitational acceleration, right? Then you can you say, okay, what is the stress here? Well, the stress actually is proportional to viscosity times strain rate, and you put the viscosity here, and the strain rate in this case, we basically kind of say, okay, assume the fluid motion or the drag of the fluid motion kind of decays over a distance of L. Then basically the strain rate can be estimated as V over L, right? And then if we assume L is on the order of R, then we just replace L with R. And then you basically have stress can be related to the viscosity and the speed, V and R in this equation. And then the C here is a constant, okay? It's some kind of arbitrary constant. It's probably on order of 1. Then you basically put this back into this force balance equation. You come up with the speed that basically is giving, like, with this very simple expression here. You can see that if you have large density deficit, then the larger speed you will have for the sphere, right? And also it's actually proportional to the radius square. So it's very, very sensitive to the size. So the larger the sphere, and then the larger the rising speed. And then the viscosity actually is kind of retarded motion. So the larger the viscosity and the smaller speed. Okay, and this is actually a very, very famous equation if you want to know the Stokes sphere velocity. This is really given by here. Okay, so then of course we know that the delta rho can be written as the thermal expansion effect, and you can put this back. You got so the velocity actually it becomes this expression. Okay, right? So now let's actually consider this a little bit further. So we know that this is the speed for this rising sphere in terms of deficit of density or temperature and other terms. Then we say, okay, for this, if this is the speed for the sphere, then let's say if we ask the time, what time will take for the sphere to rise over distance of r? Okay, then of course that's easy. That's just simply Ta equal to r is the distance that the sphere travels over the speed, right? So there's that time scale there. And so you can put these terms in here, put the V in here, you actually get this expression, okay? So now let's actually ask another question. That is actually the time scale for thermal diffusion. We see that there's actually delta T here, the temperature anomaly, right? And we know the thermal diffusion always work to dissipate the temperature anomalies, and so in doing so, it actually dissipated the buoyancy, right? And so we know we already talked about. Remember the Kelvin problem that we talked about there? We kind of said that there's a thermal diffusion length scale that is proportional to square root of kappa t, right? T is the time scale here, and so you can rewrite this. Basically now you ask a question: what is the time it takes for thermal diffusion to occur over a length scale for r, right? And that is if you have temperature anomaly of within this sphere of size of r, and you say how much time will take for thermal diffusion to dissipate the temperature anomaly away, and then that time scale is a Td, it's proportional to r square, the length scale square over kappa, right? So, and of course now so if we actually want the convection if we want to actually sustain the convection or sustain the motion of the sphere, and somehow the thermal diffusion must be slower, the process must be slower than the motion itself, the time scale of the sphere, right? Otherwise, the sphere cannot move. If the thermal diffusion is too efficient, then the sphere cannot really travel far enough before all the buoyancy will be dissipated away, right? So if you want to sustain the motion, somehow the time scale for thermal diffusion must be longer than the time scale for this advection. And if you actually set up you put all these two terms back in here, and you actually will see that somehow this number, this group of numbers, must be greater than something, some constant C prime. And of course, if you look at what this is, the sort of right-hand side or left-hand side, you actually will see that is exactly the Rayleigh number, okay, for the system. And so this is why we're saying that, from this analysis of a simple, rising, sort of sphere, we can argue that really, if you want to sustain the motion of this sphere in the presence of thermal diffusion, and somehow if you define a number called Rayleigh number, this Rayleigh number must be bigger than some constant for this to happen, okay? And of course, you can call this as constant C prime as a Rayleigh number, critical Rayleigh number, and that essentially is a sort of simple argument that we have here. Yeah.
So the way you did it is this force balance is basically comparable unity. So how do you get it to 1,000?
Well, that's actually you'll have to do some analysis to get that 1,000 number. We'll talk about that number just now. Okay. So I guess I showed you this already. It turns out that I sort of said that this critical Rayleigh number is about 1,000-ish, right? It turns out this number actually, I just said 1,000-ish because really there are other things that actually affect this number. For example, the boundary conditions. You use the here I showed the free slip boundary condition for the top and the bottom. And if you use like zero velocity boundary conditions, you'll get a different number for this critical Rayleigh number. It also depends on how you actually perturb the system. If you perturb at a long wavelengths versus you perturb at a short wavelengths, and then the convection will also require different critical Rayleigh numbers. Okay, and this is actually all. If you want to be very precise, you can. Like Turka Schubert actually gave a very nice analysis of this. And actually, they even showed that this critical Rayleigh number, I guess for this simple system, is really given by this simple expression. There's a pi there, square, and this kx here is really the horizontal, the wave number at which you perturb the system. Okay, so the lambda is essentially the wavelength. And so you can actually see this line basically is this actually this equation, and you can see that for the wavelengths that varies significantly here in this horizontal axis here, and you can see the critical Rayleigh number basically is around thousands each. Okay, a few thousand at most, right? And so you know that of course if you have a system with Rayleigh number above this curve, then that system is unstable. Otherwise, if the system actually is stable, really, right? So this is really give you this critical Rayleigh number, okay? Okay. So now actually I'm going to show you some animations. This is all computer modeling, and so the first case I will show you is a case with Rayleigh number 10 to 4. So we know it's bigger than this 1,000. So we know the system is unstable. And so this is I have this 1 by 1 box here, right? And showing the colors are temperature, blue cold, red the hot. And so initially I have this temperature that kind of increases with the depth, and I actually introduce a perturbation to the system. So you see the the contours, or the temperature contours are kind of initially tilt, right? So that's sort of initial perturbation I introduced here. And the question, of course, that we have here is that if you have a convection, and the convection will basically take your perturbation and then amplify that, okay? So the system goes unstable, amplify the perturbation, and then the convection will actually really get sustained. And so I want you to see that what actually happened, okay, in our next. So now you see, and this is a case where you perturb system with a Rayleigh number that is bigger than the critical Rayleigh number. This convection will initiate and really got sustained, and you can run this into basically forever. And this is, and you have this convection cell, and basically the cold down warnings, hot up warnings, and and so this is what happens when you perturb system with a Rayleigh number that is bigger than the critical Rayleigh number. Okay. This is good.
So what do you mean by perturb?
Perturb that basically is like I add at t equals 0 that time equals 0. I add you can say add a noise to the system, but this noise is not a random noise. Actually, this noise got some particular wavelengths. Okay, and so this wavelength actually is basically is half of the box. So this is half of the length of the box. That's sort of the initial perturbation I introduced to the system. And then since the system is unstable, it actually will take the perturbation and they amplify that. And so that's actually what happens. Okay? And so now I want to actually show you this case where the Rayleigh number is 500. We know it's less than 1,000, so the system is actually is stable. So it's already, the animation already start. This is sort of the same perturbation that I introduced for the problem I showed you earlier, but the only difference is Rayleigh number. Rayleigh number now is smaller than the critical Rayleigh number. One thing I want you to see is that now this is 300 time step, 360. I want you to see that, let's see, we'll start again. Oh, now 0. So at t equals 0, you see the slope is more steep. But with time, it's different from the convection, the unstable case. Unstable case takes the normally and start to stir, right? Amplified. Whereas in this case, where the system is stable, at t equals 0, the temperature distribution initially is more steep, and then with time, actually, it's kind of going back horizontal, right? So the noise got destroyed or decayed away with time, and the convection never really developed in this case, okay? Yeah, I'm sorry about that. And so, in order to, the vectors showing is not is normalized only by the maximum at the given time step here. So, actually, with time, the vector for this case, the vector length actually should decrease with time. But I guess that actually is a problem that I should have corrected this. So. Do you see this? I guess I just want to get this feeling that how, when the Rayleigh number is less than critical Rayleigh number, this initial perturbation kind of decays away, and then basically, if you imagine some kind of temperature contour, initially it's more steep, like here, then gradually that temperature, kind of the temperature contour became flat, then the system became essentially a purely conductive state, right? Okay. So, yeah, you're all going to have a chance to practice this afternoon. You're going to see by yourself, with your own eyes. Yeah?
I don't know that much about this, but it seems like the temperature dependence of viscosity would actually change things a fair bit and sort of enhance the instability in some sense, or because this is for an isoviscous.
That's true. This is for isoviscous. And the critical Rayleigh number, if you have temperature-dependent viscosity, and then the viscosity for the top is going to be really, really large, right? And so it became very, very tricky. You also have to worry about how to define the Rayleigh number, because you have to choose a reference viscosity to define the Rayleigh number when you have a temperature-dependent viscosity system where viscosity is varying everywhere. So I guess I wouldn't really. I mean, it certainly will change the thing. It's sensitive to the temperature-dependent viscosity. So then I guess you have to really choose the reference viscosity carefully to define the Rayleigh number, right? Yeah. Okay. So the next topic that I actually want to touch on is actually this is so-called this is scanning for convective heat flux and the velocity and how they depend on the Rayleigh number. Okay, so we already know that if you don't have convection, if you have the system that I described to you earlier, this is the depth of say a box. I guess this is the horizontal axis here is the time, the temperature, and surface is T0, bottom is TB. If you don't have convection, the temperature distribution is linear, right, across the depths. And so the heat flux at the surface, basically is given by the conductivity multiplied with the temperature gradients, right? So that TB minus T0, then divided by D. But if you have a convection, that is when Rayleigh number is bigger than critical Rayleigh number, you develop a system like this: down warnings, cold down warnings, hot up warnings. Then, we know that the interior temperature, that is the average temperature across this interior, it's about half of temperature. It's about half of the sum of temperature, surface temperature, and the bottom temperature. Okay, it's just just average. Okay, that's actually the temperature for the interior, and then we also the temperature, of course, will have to decrease to surface temperature. So there's a slope there. And then the temperature here has to increase to the bottom temperature. There's another slope there. And then this is like a boundary layers, okay? So they're actually developed thermal boundary layers. And the boundary layer thickness that we call the delta here, little delta, right? And in this case, the heat flux basically can be written as, again, conductivity multiplied with the temperature gradients. That will be here. Right, and that's interior temperature Ti minus T0 over this thermal boundary layer, little delta, right? So you can actually substitute the Ti with this expression in there, and you actually see that essentially is the total temperature difference across the box divided by 2 times the boundary layer thickness, because we have 2 boundary layers. And let's now define this Looser number, okay? Now, this Looser number is really simple. It's really just ratio of a convective heat flux to the heat flux if you don't have convection for the system, okay? So that's really, so if you put all this together, and, it's really, the Looser number is really just the thickness of the box, D, over 2 times the boundary layer thickness, okay? That's really, really simple. And you can see that since the boundary layer is thin, and therefore, this number, the Looser number, really should be greater than 1. And for the Earth, if we take delta, this is the boundary layer thickness, as 100 kilometer, so that will be the plate thickness. And since the D, for the whole mantle convection, the D is 3,000, so you will have something like a Looser number of 15, okay? So that's sort of, if you want to remember number, that's sort of, for Looser number, this is about a simple estimate for the Earth. So we also know that if you change the radian number, as I said, the Earth is about somewhere there, 10 to 7, 10 to 8, right? So now let's say if you do calculations, you show, this is a 10 to 4, 10 to 5 radian numbers. What you actually see is when you actually increase the radian number, the convection became more vigorous, that I already talked about it. And the boundary layer, the thermal boundary layer actually gets thinner. So you look at the thermal boundary layer, and this has certainly got a much thinner thermal boundary layer than this. And also, this kind of high radian number also will give you large heat output because the boundary layer is thinner, right? We already talked about this. The Looser number basically is the thickness of the box D divided by 2 times the boundary layer thickness. So you can see that Looser number is proportional to 1 over delta, right? 1 over the boundary layer thickness. And so this is why, for large radian number, we have a smaller delta. Okay, large radian number, we have smaller delta. You can see this, and also more, large, Looser number. Now, of course, it's always good to kind of develop some, simple scaling on how heat flux, or, non-dimensional heat flux Looser number depends on radian number. That is, if I tell you, if I double the radian number, can you tell me how much the heat flux increase would be, right? It would be good to have some kind of a, physical understanding of that problem. So that's actually what I want to do now, in the next few minutes. So we already, talked about this. You have a convection cell here. You have interior temperature, which is essentially the average of the surface temperature of bottom temperature. Then you also have the boundary layer thickness data here. Okay, I should say that this is really the simplest convective system, isoviscous, zero internal heating, and all that, right? So we know that now. This is back to the question that I guess Jing was talking about, about defining radian number using different scale. For example, let's actually now define what I called the boundary layer radian number. That is, you still, basically the same kind of expression, except now you use this delta, the boundary layer thickness, in the place of this length scale here. Okay, so you have delta cube, and then of course in this case we only consider the temperature difference between the interior and the surface, so Ti minus T0. So that's actually local. We call it local radian number or boundary layer radian number. I would argue that at the steady state, and this boundary layer radian number should be a constant. The constant should be, this is, sometimes you can call that a critical radian number or on the order of 1,000. Okay, I'll argue that. And so such that the delta actually is regulated by this critical radian number. Okay, so what I actually really mean here is that if somehow this boundary layer radian number is bigger than, say, this critical radian number, then the system will adjust itself to thin the boundary layer. Okay, such as like small scale convection and all that, to really remove the extra kind of boundary layer thickness delta, so such that the boundary layer thickness, the boundary layer radian number will still be kind of maintained at this critical radian number level. Okay, so if we actually accept that, then so basically that I'm saying that this boundary layer radian number really should be equal to some critical radian number. Okay, the critical radian number here, it's loosely defined as something like 1,000 each. Okay, so now if you actually take this equation and you kind of rearrange this a little bit. For example, you replace Ti with Tb, T0, and so you actually, and then you put basically you kind of multiply d cube divided by d cube, right? And then you put the d cube here, and then you basically will get expression that is since this is actually the whole thing here now, it's just Rayleigh number for the system. Then you actually get the expression that is the boundary layer thickness delta scale with basically Rayleigh number to negative 1/3 power. Okay, and this is very very sort of simple mind argument as to how when you basically were saying here was as you increase the Rayleigh number, the boundary layer thickness will decrease with the Rayleigh number to the power of negative 1/3. And since we already know the loose number is defined as the ratio of the box thickness d over 2 times this delta, then we know immediately that you put this back in there, you'll see the loose number should scale to the Rayleigh number of positive 1/3. That is, if you increase the Rayleigh number and the loose number will increase, the heat output will increase, but to the power of 1/3. And this is basically to say that if you double the Rayleigh number, let's say for the early Earth, the Rayleigh number is, let's say is much higher, and then basically we're saying that this scaling will suggest that the heat flux actually will be increased by a factor of 2.15-ish, or 10 to the 1/3 power. Okay, so this is actually very very simple analysis that we can do from this kind of simple physics we discussed here. Okay, do we have any questions about this?
Just a comment, Bill was asking about the temperature difference, and this kind of analysis tells you that for certain questions, that's actually not that important because that dependency is fairly weak. If you take a third of the Rayleigh numbers, so 2,000, 2,200, it's not going to matter. But what matters for other question is, this is always larger, much larger than the critical variable. So certain aspects of the convective plan form are not that sensitive to the Rayleigh number, others are.
Is it inappropriate for me to then sort of say that during the early Earth, the boundary layers would have been thinner?
Yes. If we think the Rayleigh number is it's much higher than was much higher than today, the boundary layer would be thinner.
With a big caveat that there's the chemical component.
Right.
So this is just thermal.
Yeah. This is just thermal convection.
You melt more, you fractionate more, you might have a whole range of other problems. Thermal.
Yeah. I said, I guess at the beginning, I'll try to stay away from the Earth, right? And so it's try to provide some basic understanding of the system. And if you threw in the composition into this, certainly will introduce a lot of complications. But I would think some of the basic fluid dynamics physics probably still true. Okay.
I mean, I guess I'm trying to extrapolate in my mind, and I'm sorry I'm pushing you to think about the Earth.
Believe me, that's always on my mind.
But I mean, when I think about the boundary layers, I think about the continents, and I think about the D double prime layer, and they're about the same thickness. And they're probably its maximum thickness today. They would have been thinner in the past.
Yeah, I don't know about the continent because you have this the composition certainly there played important role. You talk about the cratonic lithosphere, for example, as a deplete and got this composition of buoyancy there, and that probably will stay unless you kind of destabilize, right? But if you talk about oceanic lithosphere, that would be better.
And so the thing to realize, this stuff works really well for the oceanic lithosphere. Yeah. For continents, not so much.
Right, but I would assume that the bottom of the mantle is responding in a sort of similar way.
The bottom.
There may be chemical things down there that are like the continents, but the overall structure and behavior must be appealing more to like what's happening in the oceanic plate layer.
Yeah.
That it must be a somewhat uniform thickness as a boundary layer.
I mean, another thing that Shijie is probably going to talk about is that this symmetry, right? There's two ways of breaking it, hot and cold. One is what we already talked about, the temperature dependent viscosity, which is going to give you a different local Rayleigh number. Another one is the degree of internal
heating.
Shijie has demonstrated really nicely. If you purely heat internally, you get the red stuff goes away, but then it won't close. So there's another way of getting an asymmetry in the boundary layers.
Yeah.
Just thermally.
Yeah, we'll have a lot of chance to talk about the complexities. And I'm pretty sure.
What's the regime the Earth is in? So this plate tectonic like now, but you can go back and make these arguments. But plate tectonics goes episodic or into stagnant layers raised earlier. Even briefly, then the secondary structures can be quite different.
Well, I mean, that's just asking the response of the boundary layer as opposed to the fact I was asking more about the presence of the boundary layer, right?
It's whether it's how you define a steady state. If you go into an unsteady regime, over what time scale?
I just wanted to throw an idea out there, which is that, you talked about the lithospheric roots that are under the Archean cratons, but if you think about where those were formed, it's very far from clear to me that they were formed under continental material. If their residues of very high degree melting, which goes hand in hand with the idea that the Earth was hotter in the past, and therefore they were formed during mantle melting. And whether, we don't know what sort of environment that was, but it's probably not going to be under a continent. And so they were probably formed in an area that they aren't presently residing.
Mm-hmm.
So mantle melting was forming these residues, and now they're sitting underneath continental crust.
Right.
So it didn't form the way it looks today. It couldn't have. I don't see how. Well, and Rick might have other ideas. We can hear from him.
And so did we then fractionate preferentially at this location?
Say it again.
Did we then fractionate preferentially at these pre-existing locations?
I mean, the fundamental observation is that these residues that sit underneath cratons are so melt depleted that the melt that's complementary to them had it been something like a komatiite, which we don't see in the continental crust, that's overlying them today. So there's this even bigger problem. We have this problem for the continental crust in general, which is that, the building blocks of the salt, but that's not what the continental crust is. That's an even bigger problem in the Archean because we have these residues that have a complement that we don't, a melt complement that we just simply don't see in any abundance in the cratonic crust.
Right. So you somehow make cratonic continental lithosphere before you make the continental crust.
Well,
How do you
you've got a
explain?
mismatch between what's in the root today and what's overlying it. They are not complementary to one another. And
But
the
Roberta,
question is
how do you explain that they're one-to-one correlation, right?
Well, it may be that the reason we have cratons is because that's the part that was preserved, and that's because it has this root underneath it. But I don't know how these roots form. I really don't. And it's a big problem, I think.
Yeah. I mean, these proto-cratons are really helpful in getting subduction going. And if an arc is where we make a complementary crust, so there is a relationship, right? And so one way to start plate tectonics is to have somehow this buoyant thing wants to sort of maybe spill over a little, then you get subduction at the edge.
I mean, if the melting occurred adiabatically, then in fact the residue should not be pure Hardsbergite. It should be Hardsbergite at the top, and it should get progressively less depleted as you go down. And that's not what we see in the cratons. We see pretty much Hardsbergite from the moho down to near the base, and then there's some stuff happening at the base which could have been much later. So that's also a problem. I'm sorry, I don't have an answer. But it's an observation. I mean, it's a fundamental observation.
Yeah.
By the way, Roberta, isn't somebody suggest there's something fall off in the denser material basically in the
That's one way to
part
do
of
it.
lithosphere?
And you have to have the denser material falling from above and from below.
Below, yeah. So it's gone. We don't know.
Well,
But how confident are we of the composition of the lithosphere mantle?
pretty confident.
Pretty confident.
Yeah, we've got samples that come up in kimberlite, and we have a pretty good range of depths. And when you see what we call lurzelite, which means it's not completely melt depleted, usually those are secondary. They've been formed by taking Hardsbergite and putting stuff back into them.
And we were talking this morning about sampling. Is there not a sampling issue there as well?
Well, I mean, there's always a sampling issue, but what you can do is you can try to derive pressures of equilibration, and when you do that, you can see that you have have a sample in some cratons, like the one that T studied as a PhD student in Tanzania, one of my favorites. We had samples that went from really sub-moho, because they still have spinel, true spinel, so that's pretty low pressure, all the way down to what we think is the current base of the lithosphere. So that was a pretty complete section, and it's quite refractory. In Tanzania, it's refractory down to 130 kilometers or so, and then it starts to get a little less refractory, and we're not exactly sure, what that lower stuff is, when it formed.
I guess, the melting, I think if you talk about the interface with geodynamics, correct me, Thorsten, if I'm wrong about this. My feeling is that we still have a long way to go in terms of modeling, modeling the melting process in the mantle dynamics studies with a good faith, right? I think there are models out there, but this whole, this whole process actually it's fairly complicated. But clearly it's important. I mean, it's a very important process. And I guess one thing I will kind of add is you look at how other planets work. You look at Mars and even our moon. It doesn't have, apparently, I guess, it doesn't really have plate tectonics. People talk about the differentiation from magma ocean and then subsequent Rayleigh-Taylor kind of process to sort of remove the residues and all that. It's how that actually really being put together with the Earth, with plate tectonics. It still, to me, is very, very, it's just we still have a long way to go from, But, we have 2 weeks or 3 weeks to talk about it, right? Let's see. Okay, so I guess what I actually want to do now very quickly, since we're on this, maybe I'll just throw this out to you. So we can also, from this boundary layer analysis, we can actually also develop a simple scanning for how the velocity, convective velocity, relate to Rayleigh number. Okay, if you still remember a while ago, we talked about how the Nusselt number scale with Rayleigh number, right? That 1/3 scanning, and you actually, if we follow a similar kind of idea, we can actually also develop an idea about how the velocities, convective velocities, scale with Rayleigh number. Okay, that is, if we again consider this box now, the box length is L. Let's say, okay, in this picture, the L is the same as the D, but let's say if L we consider here. If some kind of characteristic of velocity, convective velocity as a V, and then basically we know that you can look at it from this picture that the bottom solar boundary layer is almost like zero below the downwalling, right? And then with time, as fluid particles travel, from the bottom of the boundary layer, and then the boundary layer thickens with time, right? And so then we know that in this process, the boundary layer thickness really should scale with the kappa t to the square root, right? And so, further away from this side, then the t is larger, the boundary layer thickness is larger, and and then we also know that on average, the horizontal velocity here, it's proportional to the length of the box divided by the time it takes for fluid particle to travel from here to there. And since we already know how delta, the boundary layer thickness, and the t relate to each other, then we can plug this back in here. Then we have a scanning on how the velocity depends on the boundary layer thickness, delta, and the kappa, and L's. Okay, so we already know from our early analysis the boundary layer thickness basically scale with the Rayleigh number to the negative 1/3 power. So if you plug this back in there, then you have this velocity scanning of Rayleigh number of the positive 2/3 power. Okay, again, this is a well-known scanning, sort of for this kind of problem. What I'm saying here is that you can get all the scanning results by considering very, very simple, sort of dynamics here. Okay, so that's just that. So I'm actually on my last example problem. So this is actually related to the boundary layer instability. And I want to actually quickly go through this. This is a sort of, I guess I added this to this list because I feel like, this community that we have here actually, is interested in the, in the lithospherical dynamics. And this is often in lithospherical dynamics, people talk about the boundary layer instability or sublithospherical instabilities. And so, this actually could be a useful discussion here, okay? Not sure. Okay, so, anyway, so just to motivate this a little bit, and we know that if you look at the present-day Earth, ocean depths and the heat flux, you plotted them, against seafloor edge, and this is sort of the well-known plot: the ocean depths, versus the seafloor edge. Of course, ocean depths increases, as you move to older oceanic lithosphere. Then there's and also if you actually look at the heat flux, it actually shows similar, trend. That is, the heat flux actually decrease as you go to older oceanic lithosphere. And this is just a zoom in of older oceanic lithosphere. And the lines here, the dashed line here and the solid line here, they're actually a prediction from this so-called half-space Cooling models, okay? As you can see, the half-space Cooling models explain observation reasonably well until some age, like about 70 or 80 million years, old seafloor, right? So just very, very quickly, and we already talked about this model earlier. That is, if you actually ask a question, if you take a column of material at the mid-ocean ridge, which is uniformly hot, and then you kind of carry that column away from mid-ocean ridge, and in the same time you cool from the top, and then basically you'll form this boundary layer, thermal boundary layer again, and the temperature as a function of age, seafloor age, and as a function of depth, basically is governed by this simple equation that actually we talk about this from Kelvin's model, and then the solution is very easy to get for the temperature. And then, of course, we know that you can actually compute the heat flux from this, and you can compute the thermal substance, and that you can use. That you can actually then come up with the prediction for heat flux and the ocean depth versus varies with age, and that actually really explained the observation reasonably well, right? Until when the seafloor age reached to 70 or 80 million years, and then of course people have suggested that this cooling of the oceanic lithosphere cannot go on indefinitely, and that is when this boundary layer thickness increases to a certain thickness, then this convectivity will become unstable. Then you may actually develop this so-called small-scale convection. Okay, that is. So the idea, of course, here is that we know the boundary layer thickness actually was thickened with time as a function of time. There's kappa square root of kappa t here. And if you actually put this into this boundary layer Rayleigh number, and you will see that as delta increases, and the Rayleigh number will increase, right? And we already argued that this Rayleigh number is regulated by some critical Rayleigh number, right? So this Rayleigh number cannot increase indefinitely, and therefore there is a chance that when at a certain time t, and then the delta will be sufficiently large, then this Rayleigh number became larger than the critical Rayleigh number, then you will start to develop a small-scale convection, okay? So I want to actually show you a computer simulation of this process. And so what you're seeing here is this is the depth, this is the horizontal dimension, the width. And so this is at t equals 0, the everywhere is red, means hot. And then I also will show you this is the heat flux versus the time. And then this is actually showing here is the horizontally averaged temperature versus the depth. And you actually see two lines here. And one is the dashed line, which is a prediction from the Cooling model. And the solid line is actually the model output. Okay. Initially, they agree with each other. And then once the small-scale convection set in, they start to deviate from each other. Okay. I want you to actually kind of pay attention to that. Whoops. I guess I hit the wrong button. Now you see the cooling, the boundary layer thickness increase, and so they really match with each other, and then boom, you start to hit the boundary layer thickness reach to a certain level, you start to see small-scale convection settle in, okay? So then that's actually when you start to see the deviations between the half-space cooling model prediction for heat flow and the numerical modeling for the heat flow, okay? So, well, you can actually, for this problem, you can actually kind of, I guess, you can actually, I'll say, determine, kind of quantify the onset time, and you actually see how this onset time scale with the Rayleigh number, okay? And this is actually well-known negative 2/3 power. That is the larger Rayleigh number, and the shorter time it takes for the small convection to happen, right? And so, so this is a sort of well-known scaling that you can derive from numerical experiments. And I would encourage some of the students actually. This is one of the tutorial problems. If you're interested, you can actually do that yourself. Yeah.
It might be interesting to know that this goes the other way than what would be expected from the anomalies of the sea floor age, right? You get more heat in.
Yeah. So you
just because people, when you talk about deviation from the half-space cooling, people might be thinking, oh, the plate model and this whole story about the sea floor.
Yeah. No, I didn't want. We can. That's a very interesting topic, and I didn't want to get into that. Yeah. And so I guess actually I want to just very quickly go through. Sort of using the physics that we discussed so far in this lecture, I want to actually kind of chat very quickly about how we might actually analyze the problem to get the scanning for the onset. Okay, and so let's actually again define the boundary layer Rayleigh number, right? The data here. We're saying that basically at onset, right? We want to actually at onset, and this boundary layer Rayleigh number should be equal or roughly equal to a critical Rayleigh number, right? And we also know the boundary layer thickness should proportional to kappa t square root, right? So that's already been discussed. Now we're saying at onset time, when t equal to tau c, which is onset for this small scale convection, the boundary layer thickness is equal to some, say, critical boundary layer thickness, let's say delta c, right? So we're saying that at instability, then this boundary layer Rayleigh number is proportional or equal to this critical Rayleigh number. And now what we can do is to basically carry on this analysis a little bit more to say, okay, since we know this is true, right, we can actually solve. We take this, we can solve for delta c. That is essentially just rearrange the terms. You get the boundary layer thickness at onset that actually is given in this form. We also know the boundary layer thickness at onset should also be equal to kappa tau c, right? That's basically take this expression. And so you net these two equal to each other, and you get actually the tau c. That is onset time for small scale convection would be proportional to Rayleigh number to negative 2/3 power, just like a numerical model predict, okay? And so this is all very, very simple analysis. That you just based on what we discussed today, and you actually can get all this interesting scanning that you don't really need to run convection models. You can still understand it, okay, to the first order. So I guess I'm sort of running out of time. So I said I promised that I actually will show you one slide to basically talk about the challenges, complications, and this is that slide. And so mantle rheology, yes. I talked, all I discussed so far today is all based on constant viscosity. And the mantle rheology, of course, is the temperature, stress, composition dependent, right? And also got a brittle deformation. Especially the brittle deformation could be really fundamental if we want to understand the emergence of plate tectonics. I think my position on this is that we don't really know how to do that yet. Okay, and you see models, and I think they're actually I'm not sure about those models. Okay, so the mantle rheology, of course, is very, very important for for understanding plate tectonics and also for understanding the mantle structure formation as seen from seismology. And also the heating source that Thorsten actually kind of mentioned earlier, that we know this heating source is actually inhomogeneous distribution in both time and space, right? And so, that is certainly a complication, which can be important for understanding the plume dynamics and melting and all that. As I said, I just want to spend 1 hour to talk about the fundamentals, the simple concepts. Then we have the rest of the, 3 weeks or 4 weeks to talk about the deviations from that, right? So I guess this is sort of a quick summary. I kind of reviewed some of the history of the mantle convection studies. I also outlined some of the basic physics of mantle convection. And so then this afternoon we're going to do the tutorials, right? And what we're going to do there essentially is to learn how to use this 2D convection code, SICON, using this VirtualBox software. So I have the VirtualBox software here, and I don't know how many of you actually download. How many of you download onto your own computers? Okay, well, not that many. So this is about 2 gigabytes. Yeah, 2 gigabytes. And so at some time before the tutorial, hopefully, maybe I can make a few more copies of the, on the memory stick so we can distribute it. Well, actually, it will take about 6 minutes or 5 minutes to download this.
Is it available on the wiki that they can download?
Well, it takes time to download. It's 2 gigabytes. So this is why this is faster. It still takes 5 minutes on my computer to basically copy over. I don't know about your computer. I got a pretty old computer. So if we can make a few more copies of this memory stick, then we pass it around, and then we'll get this started. So hopefully before the tutorial. And we're actually going to solve, for the tutorial, I actually will discuss 3 problems, about how to solve the 3 problems using the computer code. And basically, you can see it. Determine the critical Rayleigh number, and Rayleigh Rayleigh number scaling, and the onset time. If you pay attention during my lecture, and you actually will be okay, right? Yeah?
You talk about mantle convection. Actually, I have a question on the crustal convection. Can you could some part of lower crust, in particular the lower crust beneath Tibet, come back?
Well, depending on the viscosity, right?
Yeah, but can you tell me what the viscosity would be?
Well, you have to kind of take the critical Rayleigh number, and then kind of, let's say, assume it's 1,000, and resolve for the viscosity. So you have to assume the temperature scale.
I can tell you what temperature is like.
Yeah.
I have no idea what the temperature would be greater than 650 in the northern.
I guess upper crust is almost impossible to. So it's probably you probably have about a couple hundred Kelvin temperature that is available. Yeah, that's maybe a few hundred Kelvin. But I guess what is relevant is really the temperature difference across the lower crust, right?
700 to about 1,000.
Okay. Let's give you 300.
It's pretty much lunchtime. We can continue when you have the tutorials.
Yeah.
Does everyone know where lunch is? No. It's in the cafeteria between the student dorms is just south of you. The faculty dorms just north of you. Crossroads. It's sandwiched between the 2 dorms.
Can we leave our computers here?
Is this going to be locked? I suspect it's not going to be locked.